Hello everyone, welcome again in Eng-Man YouTube channel. So again, we will continue our learning on reservoir simulation using tNavigator software, and we will use sample case from tNavigator. We can learn a lot from those cases like the one we have right now. So in this case, we will perform alternating water and injection gas to improve oil recovery, and we will use CO2 as the injected gas. And later on, we will expand the case with CO2 dissolution. So you can also connect it with CCUS topic, carbon capture, utilization, and storage. Okay, where in this case, by dissolving the CO2 into the brine, sort of we are storing or sequestering the CO2. Okay, so first we will start by introducing the model. We start with initial properties, the size of block X in X direction, Y direction, Z direction. The depth, so we are located at this depth around 6,000 feet. This is the top net to gross, okay, net to gross of 1 throughout the reservoir, so it's good. Porosity, we have homogeneous reservoir from porosity point of view, but permeability varies a little bit. Not a little bit, but yeah, we have heterogeneous permeability, X direction, Y direction the same, and Z direction. And as you can see, yeah, maybe you can, relate the permeability in Z direction to the permeability in X direction. Because usually permeability in Y or Z direction, I mean, is a fraction of permeability in X or Y direction. So vertical permeability is usually a fraction of the horizontal permeability. Okay, so that's for the initial, that's the main thing. And as usual, we can expand the file here. So click on File, check the master data, and I will go through. I will show you the keywords, especially the most important ones. Okay, run spec as usual. tNav control, model E3. So you can relate the E3 with Eclipse software for simulation as well. And when we use E3, we use that for compositional modeling. Okay, and this is the title where we will call this topic water alternating gas injection using CO2, the injected gas. tNav control smooth RP, so we will use smoothing for the relative permeability, but actually it's not the most important thing here. And dimensions, this is important. So 9, 36, and 40. So basically we have 9 blocks in X direction, 36 in Y direction, and 40 in Z direction. And you can count it. So first we check X direction. So it's like this. And you can count it with me in X direction, right? We will have 9 blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 36, you can count from the left side to the right side, and you will count as many as 36 grids. And in Z direction, you will have 40 blocks from the top down to the bottom. Okay, so that's what dimensions here means. And field, we will use field unit. We are going to use water, and this is the dimension for the data for the equalization. Okay, and if you check fluid properties equilibrium, we only have one here, one package of equilibration or equilibrium. Okay, and well dims, this is the setting for the dimensional for well data. And n scale, so yeah, I used this, dash, two dashes, so it means that we will not use this. Okay, that's not really important in this case. But basically, n-scale means that we will use n-scaling for the relative permeability. Nadir, it means that the scaling will not be based on any direction. And reverse means it is reversible. Okay. And comps, we will use 5 components in our compositional modeling. And you can add, right now you can check it by opening these components properties. Okay, 5 components, CO2, C1, N2, C2, C3, C4, C6, and C7 to C12 plus. Okay, so of course you need to do PVT analysis, PVT matching, PVT modeling, PVT lumping before you use the fluid, the generated fluid, the simulated fluid into the simulation, into the reservoir simulation. Okay, but again, we will use what is provided by the tNavigator in the form of example case, and that's it. We have 5 components. Okay, univout, it's about, saving the calculation results as E1 or E3 binary files. So E1 means black oil modeling, E3 compositional modeling, referring to the term from Eclipse. Okay, and univout also sets mode of the output, okay, for restart and summary files. But basically, it's about saving the result. And you can use this keyword. Okay, and then start of the simulation, June 1st, 1999. And then the RACDIMS. So RACDIMS is also, it's like WELDIMS, TAPDIMS. It's basically, about the region, the dimensional setting for the region, okay? And then the grid section. So whatever we have in our grid, we will take the data from this file. Includes grid.inc. .inc mean include. So we can check what we have inside the grid. So here we have, the initial, all of these data are taken from the grid file. So let's check it. Grid, this one. Okay. So init, we have keyword init for the initialization. And this one PV means we will only allow the grid block that has pore volume minimum this value. Okay, so we will allow any block with a very small pore volume, but we will reject anything below this pore volume. And then agnum, so we will activate this one, 12,960 grid blocks, which is the result of the setting, the dimensions for our modeling, which is 9 multiplied by 36 multiplied by 40. So X multiplied by Y and multiplied by Z. And then this one, dx, dy, and dz, basically the block size. So as you can see here, 8.2 multiplied by 10, right here. This will be applied for all these 12,960 grid blocks. So basically the dx, the size of the block x, I mean block size along x, sorry, is 82. And you can check it here. You see, everything will be 82. For y, everything also will be 82. But for z, everything will be 1.625. And you can see in our code here. Okay. And then porosity will be homogeneous, 19%. You get that from here. I can, of course, change it to 0. something, right? 0.25, 0.22. And then I can reload the model and you will have everything will be 0.2 something as per input. Okay, and then this is the setting for permeability in X direction, permeability in Y direction, and permeability in Z direction. Okay, you can expand it, you know. So basically we provide, for example, this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 4 rows. Basically, we are imputing the permeability in Z direction for the 40 grid blocks that we have. So like this one, the first one is 0.03 to 55. So if you check at the permeability in Z direction, okay, and then grid block Z number 1, 0.03255. And then for the second layer, 0.05815, you basically get that from this. And then and so on and so forth. Like 0.05065. 0.05065, right? So that's it. And the same thing also for block X. I mean, permeability in X direction, you have 6.51 because we input 6.51 here. Okay. And then what else? The tops located at this. Okay, so 6,000. Let's check it out. The top, right? 6,000. Okay, so that's for the grid. Very simple. Okay, so, and then what else? Now let's check again the master data. Edit. Okay, basically there is no editing. So if you open this file, it's empty, but yeah, you don't need to use this as well. Now properties section, props, the keyword is prop. Everything for the properties are taken from this file, props include. So let's now open props. We only have one, this one. Okay, so let's check it out. So this is for the rock compressibility, the pressure, and the value of the rock compressibility. Again, we will use 5 component. The EOS that we will use, the equation of state, Peng-Robinson, correction or correlation, and then this is the setting for standard convection for the temperature and then the pressure. This is the component names. We define it here, CO2, C1, N2, C2, C3, C4, C6, and this one. You can rename it if you want. And after you perform the PVT matching or PVT modeling, okay, you will get several properties. Like this one, we have critical temperature. This is the, this is the keyword, and then critical pressure, critical volume, and then volume shift. Okay, critical volume, eccentric factor, molecular weight, and then this is the composition, boiling temperature, reference temperature, specify fluid density at the reference condition, component paracores, binary interaction binary interaction coefficient between components, reservoir temperature 212. And then for the PVT, we have here the pressure 3000, the reference pressure, and then the formation volume factor 1.03, and then we have the compressibility of the fluid, and lastly the viscosity. And then this is again, still the property, but now we have the relative permeability. We have 4 columns. The first one is water saturation. The second one is relative permeability of water, relative permeability of oil, and then the capillary pressure. So we can check it. Fluid properties, and then RP, water oil. You can compare the data with what we have written in the note. So 0.12, 0.12, capillary pressure 36, there you have, and then RP water 0, RP oil 0.5, all the way down to the bottom, 1100, 1100. Okay, good. So that's for oil water system. And for the oil gas system, we will use this table. Okay, so basically, I can also give you a practical advice. So if you don't want to perform, let's say, PVT matching or PVT modeling because you're very lazy, for example, you can just take an example case like what we have here and then copy everything. Okay, just assume that whatever we have here is also applicable in your case because you maybe want to do study example, right? Not the real case, okay? You just want to study, you just want to make a modeling, then you can copy everything here and then use it as the properties file and then include it in your model in your simulation and make sure that your working limit or working condition is actually relevant to what we have here. So like in this case, if in this model we are using pressure of 30 or of 3000, then in your model you also work around that pressure as well. Okay, so what we have here can be applicable for your case as well. So that's the main thing. But of course, the best thing is you need to do the fluid modeling, fluid matching, something like that. And then solubility data. So this is for the CO2 dissolution. And then this is the, Connaught water saturation. So let's check it out. Okay, do we have here? Or in this case, it is also called critical water saturation. Okay. And then we also have critical gas saturation 0.01. We set that using this keyword. So all the 12,960 grids will have this critical gas saturation and critical water saturation and critical oil saturation. So this critical value will be used. And maybe we can compare that with what we have in the table. Okay. So for gas, okay, let's compare it with 0.01. Yeah, a bit different with the table, but basically because we put these keywords after the relative permeability data table, we will still use this one. Okay, this will still be applicable. And so, although here you have saturation 0% or zero fraction saturation, you already have, wait a minute. Oh, this one is RP for oil. RP for gas is this. Okay, so based on this, the critical gas saturation is 0.01. So at 0.01, the relative permeability for gas still 0. It starts to flow right at the critical saturation. So that's also, it's still relevant with this table. And then also for the water, let's check it out. For the water, we say that the critical is 0.17. But here, even at 0.15, we already have water flow with this relative permeability. Okay, so everything here for the water will not be regarded, but this keyword will be regarded. So at 0.17, water saturation of 0.17, we still have no flow of water. It just starts to flow. So if your saturation is greater than 0.17, then it can start to flow, and the model will use this table above 0.17. And that's also for the oil. Okay, so here 0.2. So at water saturation 0.8, we will have no flow of oil. So the relative permeability of oil will be 0 here. So this row number 15 is good. Okay, so that's for the critical saturation. And this is the minimal water saturation 0.12, match with this table, SWL. Okay, so that's for the properties. And then what else? We have regions. So we will get the data for region from this include file. Let's check it out. Sorry if I take some time because I want to go into the basics so that you can understand. Regarding the perforation, regarding the simulation of the water alternating gas injection, we can do that later on. Region. Okay, so we have this region, set num, regioning based on saturation, only one. Regioning based on PVT that is used, only one. For equilibration, only one. And PMA num. So let's check at the region, grid properties, region. PNum is actually pressure maintenance region, only one. And then FIPNum is, yeah, fluid in place number. So we only have one. So everything, we don't have any zonation that is distinct from any other region. We only basically have one region for everything. Okay, so that makes life easier. And then solution. Solution, we will take that from init. Okay, let's get the solution init. Okay, so this is for the equilibration setting. Okay, we have equilibration. So fluid properties, equilibrium. Okay, this is for the equilibrium or initialization. And then this is the datum depth, and outsol is basically the additional data that we want to be generated by the model, by the software when we perform simulation. So we want saturation of oil, saturation of gas, saturation of water, and so on and so forth. Formation volume factor for oil, for gas, and then right, BO, BG, BW, relative permeability. V, I think, is viscosity, and pressure, and so on and so forth. So that's for init. Summary. Okay, so everything that we need to be produced by the software is written here. Of course, I'm not going to talk about everything here. So if you are interested, you can go to the manual and read it for yourself. And one of the most important thing here, before end, this will end the master data, is actually includes. And within this include, we will set the alternation between water and gas injection. So let's check it out. So let's go to this file, schedule include. Okay. All right, so let's start with this one is the reports scheduling. This is the, the default setting usually. Run control. So this is the delta time max original 100. Well specs. So now we will define two wells. The first one is injector 1 and producer 1. This is the group name G2 and G1. That's not really important. This is the location in I and J direction. So injector will be located at grid 1, 1, and then the producer at 936. The, the fluid injection, of course, water and producer oil. And this is the depth. Okay, so let's check the location. Okay. So injector located at cell 11 here, 11, and then producer 936. Okay. And then this is the trajectory for injector and trajectory for producer. And if I uncheck the grid, we actually have horizontal well. Okay, so let's continue. com.md is the completion using measured depth. So for the injector and producer located at here, status open, and maybe we can check it here. Right click, show well, or not well, edit well. Okay, so basically this is the trajectory. Okay, and then connection. So 0.16 is the diameter. Okay, and what else can we say? It's the trajectory connection. Status open. Yeah, that's it for the well. And for, let's check here, depth. Okay, and then yeah, basically here we have defined that the open interval will be at this, but in measured depth for the injector and for the producer. So producer here, the open interval start from 6007. So that's why we have here 6007. And because it's measured depth, if you calculated this location and you add it with the length of the horizontal section, then you will get this 8877. And that's also the same thing for the injector. So let's check this one for the injector. It's located at 0. Okay, 0.51, but the opening start from 0.06064. Okay, so this one, or maybe I think that's already correct, because if you see the axis 0.0, I mean 6065, which is located very close with 6064. Okay, so that's it. And then the setting for the producer, for the production, I mean, wconprod, the name of the well, start with shadin, controlled with bottom hole pressure, and then we can check it at the schedule, of course. So you see here first well specs here, just as what written in the dataset, and then com.md here you can see, right? So this one is lower measured depth for the connection and upper measured depth for the connection, both for the injector and the producer. And then we also have PI multiplier for the injector. So connection transmissibility factor multiplier 0.5. And we can find that in the data set. Let's find WPI mode, well PI mode. There. So we will use for the injector 1, the PI multiplier is 0.3, and 3 star means that everything will be perforated interval X and Y and Z direction will be skipped, will not be set. And then well production, this is the setting. So let's compare it with the data set. So this one for injector 1, start with shut-in, controlled by bottom hole pressure, surface flow rate 6,000, and 12,000 as the upper bottom hole pressure. And yeah, everything here as our constraint is actually taken from this. So yeah, that's the thing. And you can see here we have alternating water and gas injection. So we start with at 2000, we inject gas for 1 year. And then in January 1st, 2001, we inject water. The keyword is WAG-CO2 for well injection. The injector is inch 1. And then 2002, we inject gas again. 2003, water again. 2004, gas again. Next year, water again. Gas again. The next year, water again. So that's the thing. It's quite easy. So alternating water and gas injection is not very complicated. It's just, changing from water and then to gas, water again, and to gas. The control mode the same based on bottom hole pressure, and the upper limit for the bottom hole pressure the same, 12,000, and the flow rate also the same, 6,000. And I can erase everything here, 2001 to 2007, the setting. So the only thing that will be applicable is the last time step, which is this one. At year 2000, so I will only inject gas throughout the operation. Or I can also, maybe I should show you this one. So if I open this one, I mean change it to water, and then I delete all the next WCON-inch, then the last rule or the last setting will be applicable. So this will be applicable till the end. Okay, that's the same thing if you use gas and you delete everything, then this last setting will be applicable for the rest of the simulation. We will only inject gas. But if you want to perform alternating gas and water injection, then you will switch from gas and then move to the next year. Here, water cycle, right? January 1st, 2001. Now you input water here. You write water. And then we move to January 1st, 2002. Now you come with gas again. 2003, water again. You don't need to shut the gas injection. You just put again the comment, but with water, not with gas. And then gas, and so on and so forth. The setting for the water, I mean for the production of oil, doesn't need to be alternating. So we only have one setting here. In September 1991, we have this setting. So producer 1 will be open. This one will be the oil target. This one will be the liquid rate target, the upper limit. So you will not produce greater than 6,000. And this is the bottom hole pressure. And then we continue the next year. We maintain the same keyword, the same setting. Well, producer 1, status open, bottom hole pressure as the control mode, 3,000 oil rate, upper limit, and then 6,000 liquid rate, upper limit, and then the bottom hole pressure, lower limit. Because we use bottom hole pressure as the control mode, the most important thing is the 400, not the 3 or the 6,000, right? Because the setting will be based on bottom hole pressure. That's what we set here. You can also change it to liquid rate or oil rate if you want by changing the keyword here. So let's go to wconprod. Okay, so you can change it to, for example, for liquid rate, LRAT or ORAT. But in this case, let's go back to bottom hole pressure. And then well stray. So this is for the well stream. We use it for the injection, especially injected gas. The stream name is inch gas. So we have 5 components. The first one is CO2, meaning that we will inject gas with this composition, 98% CO2, and then 1% C1N2, and so on and so forth. W inch gas, we will apply this stream onto this injector. That's the meaning of W inch gas. And the next thing is already discussed, W con inch, meaning the setting for injection, and the dates, meaning that we will move across time using these time steps. Production, 10 minimum oil production. So this is the economic limit, right? So to speak. And then this one is maximum water cut, and then maximum gas oil rate, and then stop simulation flag, workover procedure. Okay, so we will perform workover procedure when we have the water cut exceeding this value or GOR exceeding this value. Okay, and this one, prot well name plate, well list, or well list template. So basically, this economics will be applicable for all producers. But because we only have one producer with the name prot1, so this setting will be applied to that producer. So that's why we have the name here, prot and star. Okay, so everything with the name prot and something like prot1 or prot2, prot3, in case you have the naming like this and the number of the wells, it will follow this setting. The minimum oil rate, the maximum water rate, the maximum gas oil rate, and so on and so forth. Okay, and then group operation, network, no, other. Yeah, this is run control. Okay, and well stray, injection stream composition, the name of the stream, inch gas. This is for component 1, component 2, component 3, component 4, component 5. And then you combine all operation, you have this. So basically, it's not very complicated. Now, as usual, I think I'm going to show you the saturation of oil. So we start with homogeneous distribution of saturation 0.88, and maybe we can start from this average, start from this value, color by contour line, or maybe this is more beautiful. Uncheck the show grid. Oh no, uncheck the grid line, and let's run.